Welcome back. And in this last video in Kinetics 1, we're going to just be looking at the rate expression. So that's combining the individual rates of reaction to make an overall rate expression. So our overall rate equation is our rates, which is now equal to the overall rate constant, which is the individual rates constants times together, times by the concentration of my two reagents, A, B, raised to a particular power. And those powers are constant and by the order of reaction, 0, 1, or 2. So with the order of reaction, we can work out what effect changing the concentration will have on that rate. So if we double our concentration, for 0 order reaction, the rate will be changed. Double the concentration of a first order reaction, we will that will double the rate. Last but not least, if we have a second, we double the concentration, that will times the rate by 4. In other words, it will times it by 2 squared. Likewise, the same if we triple the concentration. So if we change the concentration by 3, it'll have no effect on a 0 reaction. It'll triple of a first order reaction, and it'll times the second order reaction by 9. In other words, it by 3 squared, because it's a second order reaction. So we're going to look at this in a little bit more detail. So we want two experiments where we're keeping the concentration of nitrogen monoxide constant, but we're doubling the concentration of hydrogen ions. So we're going to look at experiments number 1 and 2, because in this case, this concentration stays the same, but this concentration doubles. So we're going to look at experiment 1 and 2. Now, experiment number 1 and 2, the hydrogen ion concentration doubles and the rate doubles. So therefore, the order of reaction with respect to H is the first order, because rate depends on hydrogen ions, so the rate is directly proportional to the concentration of the hydrogens, so it's first order. So we want two experiments where the hydrogen constant, but we double the NO. So in this case, we're looking at 4 and 5, because between 4 and 5, the concentration of the hydrogen stays constant, but we're doubling the NO. So we're looking at experiments and 5. And in this case, the rate is proportional to the concentration of the NO squared. We look here, we double the concentration, but that times the rate by 4, 5 times 4 being 20. So that's a second order reaction. So the overall rate for this rate expression for this reaction is our rate constant K times the concentration of the hydrogens raised to the power 1. We quite often don't know it. It's by the concentration of the NO squared. The overall order of reaction is 3, the sum of the individual orders. And we can use this rate equation and data from the table to calculate K. So I'm going to rearrange this, and I get K equal to rates divided by the concentration of the hydrogens times the concentration of the NO squared. And I'm going to use data from the first experiment. So I've got my rate as 0.003 divided by the concentration of the hydrogen ions, 0.001, times the concentration of the NO, 0.006 squared. And I get, as my answer, 8.33 is 10 to the... Now I need to work units. Now units are very important, and they will vary dependent expression. So K does not have constant units, so you always need to state units in this expression. So we got rate divided by concentration times concentration. So we have moles per decimeter cubed per second, that's my rate, divided by moles per decimeter cubed times moles decimeter cubed squared. Well, those two can cancel. It's going to come up the top, and I get moles to the minus 2 d6 to the minus 1. And those are my units. And we're going to practice writing those out in class. Please note there is no relationship between the molar quantities and the order of reaction. In other words, you cannot look at the balanced stoichiometric equation and work out the order of reaction from that. You have to do it experimentally. So we're on page 21 of your notes, and we're looking at first order reactions and half-lives. So if we consider this concentration time graph, what you notice first of all is obviously that the concentration falls as the reaction proceeds. What we're now going to look is at the half-life, in other words the time taken for the concentration to halve. So the concentration drops from 4 to 2 in 17 minutes. That's its half-life. The concentration drops from 2 to 1 in a further 17 minutes. And the concentration drops from 1 to a half in another 17 minutes. Now this indicates that this is a first order reaction because it has a constant half-life. So the time taken for the concentration to halve remains constant. 4 to 2, 2 to 1, 1 to a half, each take 17 minutes. Constant half-life means a first order reaction. So in the last bit of the notes we're looking at page 22, and we're just looking at these definitions which you need to be able to write out in the exam. So the rate of reaction is simply the change in concentration over change in time. Now that time could be minutes, seconds, nanoseconds, days, whatever, but you need some sort of time unit in there. The rate equation is given by the expression rate equals K times the concentration of A raised to a power times the concentration of B raised to a power. Now these have to be found experimentally and are found by measuring the rate of a reaction. The order of a reaction is the powers to which those concentration terms are raised. So little a and little b in the rate equation example are our orders of reaction. The overall order is the sum of the individual powers. So the overall order of reaction for the equation would be little a plus little b. The rate constant K is that constant of proportionality, linking the rate to the concentration. We're going to look at this in a lot more detail in Kinetics 2, when we're going to be looking at the Arrhenius equation and how that relates to the rate of the reaction. Last but not least, the half-life, the time taken for the concentration of the component to drop by half. And this will always be constant for a first order reaction. So that finishes Kinetics 1. There are a few more experiments which we haven't demonstrated, but you're going to do those in class. So until next time, take care, stay safe, bye-bye.